In the last few lectures, we studied the topological property of being connected. So we saw several examples of connected topological spaces, connected and disconnected topological spaces, and also how connectedness can be used to distinguish between spaces. To differentiate topological spaces. For instance, one of the exam questions was show that S1 is not homomorphic to the interval 0, 1. So the problems, but we did not cover all examples. So the problems of whether SON and UN are connected are pending. And these will be taken up. So for the next few lectures, we will discuss the property of being compact. But before defining compactness, let us recall the definition of Hausdorff. So let X be a topological space. X is said to be Hausdorff. If for any pair of points x comma y in X with x not equal to y, there are open sets ux containing x and uy containing y, such that I can just say u containing x and v containing y, such that u intersection v is empty. So if we take R2 and 2 points, then clearly we can make two small disks around these 2 points, and so R2 is common. R2 is Hausdorff. This picture shows. Okay, let me not write this. So here are some easy exercises. X and y, Hausdorff, implies the product is Hausdorff. do the same for arbitrary products. X is Hausdorff and Y contained in X is a subspace implies Y is Hausdorff. So the above exercises gave us plenty of examples of Hausdorff topological spaces. So in fact, we will deal almost exclusively with Hausdorff spaces for the rest of the course. So now that we know what Hausdorff spaces are, we can define compact spaces. So let X be a Hausdorff topological space. I need not have mentioned this hypothesis because from now on all spaces are Hausdorff. So we should say X is compact if for every open cover, so every time I write X as a union of open sets, Ui, if every open cover has a finite subcover, has a finite subcover. That is, there are indices I1 up to In in I such that X is equal to Uij. So for example, let's see that R is not compact. So if we write R as the union so in other words, we have the real line, there's n and there's n plus 1, and we are taking intervals of this type, and we are writing R as the union of intervals of this type, then clearly this has no finite subcover. So the first theorem we are going to prove is that the closed interval 0, 1 is compact. So proof. So suppose we have an open cover of 0, 1, P an open cover. So we need to show that this has a finite subcover. So let S be the set of x in 0, 1 such that when we take the interval 0x, this interval is covered by finitely many ui's. So note that 0 belongs to S, as the interval 0, 0 is just equal to the singleton, is covered by any ui containing 0. So S is non-empty, so we let x naught be equal to the supremum of x in S x. So first we claim that we want to show that x naught is in S. We claim that x naught belongs to S. So to see this, there is a sequence xn converging to x naught where xn belongs to S. So let x naught be in some open set ui naught. So there is an epsilon positive such that p epsilon x naught intersected with 0, 1 is contained in ui naught. So, and by the definition of convergence, all but finitely many, xn are in this set. So choose some xm in B epsilon x naught intersected 0, 1. So our picture looks something like this. This is 0, this is 1, x naught is somewhere here, this is the ball 0, 1, and our xm is somewhere here. So then 0 comma xm is covered by finitely many ui's, and the interval xm comma x naught that is contained in B epsilon x naught intersected 0, 1, which is contained in this ui naught. So this implies that the interval 0 comma x naught is also covered by finitely many ui's. So we can just take the ui's which cover 0 xm along with ui naught. So take the ui's which cover 0 xm and ui naught. So this proves a claim that x naught belongs to S. So if x naught is strictly less than 1, then x naught comma x naught plus epsilon by 2 is contained in u I naught. But then this implies that 0 comma x naught plus epsilon by 2 is covered by finitely many ui's. So this implies that x naught plus epsilon by 2 is in S, which contradicting that x naught is the supremum. So thus x naught is exactly equal to 1, and this proves that 0 1 is covered by finitely many ui's, which implies that 0 1 is compact. So as before, we can ask, what about products, subspaces? So if we take products of compact topological spaces, are they compact? If we take subspaces, are they compact, etc., etc.? And notice that, so one example we can get straight away, if X is compact, it may have non-compact subspaces. For example, so we can look at 0 1 contained inside the closed interval 0 1. This is homeomorphic to R. And so not compact. But the assertion is true for products, which is what we want to prove next, in which we need the following lemma. This is called the tube lemma. So let X be a topological space and let Y be a compact topological space. So let W contained in X cross Y be an open set which contains X cross Y. So then there is an open set U which contains X. So open set U in X which contains X, such that W contains U cross Y. So the picture is something like this. So this is Y, let's say this is compact. So this is x cross y, and W is some open set. So then what is being said is that there is an open neighborhood U around X such that this whole U cross Y, this whole tube is contained inside W. So let us see how to prove this. Given any point y in Y, there is a basic open set U Uy cross Vy containing x comma y, and Uy cross, so if x is fixed here, so Uy cross Vy is contained in W. So since the point x comma y is contained inside W, there's a basic open set Uy, there's an open set Uy, there's an open set U containing x and an open set V containing y, so we will denote those by Uy and Vy, such that Uy cross Vy is contained in W. So in our picture it looks something like this. So maybe if this is the point x comma y, so then this could be Vy and this could be Uy. This interval here could be Uy. Okay. So clearly y is equal to the union of all these y in y, v sub y, and as y is compact, it has a finite subcover. So we can write y is equal to union I equal to 1 to n. So let U be the intersection UII. So this is an open set containing X. So then U cross VYI is contained in UYI cross VYI, which is contained in W, which means when we take the union, U cross VYI is contained in W, but this implies U times the union is contained in W, but this union is just Y. So this proves it. We will use this lemma to prove this theorem. Let X and Y be compact topological spaces. Then the product X cross Y is compact. So proof. So let's say we are given an open cover. Be an open cover. So let us fix an X in X. Right? So then X cross Y is contained in this union. So as X cross Y is homeomorphic to Y, it is compact, and so this is contained in a finite subcover. So we can say X cross Y is contained in the union I belongs to some I sub X Wi, where I sub X contained in I is a finite subset. So by the previous lemma, there is an open neighborhood U sub X of X such that U sub X cross Y is contained in this finite union. Okay, now we let X vary. So this happens for all X. So this happens for or this can be done for all X. So this implies the UX's form an open cover for X. So by compactness of X, there is a finite subcover. So we can write X as UX1 union UX2 union. So then X cross Y is equal to UXI cross Y, which is contained in union of the IXIs WI. Because each UXI is contained in the union of I in IXI of WI. So as each IXI is a finite set, so this implies union of is finite. This implies we have found a finite subcover. So this completes the proof of the theorem. So as a corollary, we get that when we take the product of the interval closed interval 0 1 with itself n times, is compact. So we saw that uh, any subspace of a compact space need not be compact, but if we take a closed subspace of a compact space, is compact. So let us prove this. So let Y contain X be closed and X be compact. So suppose we are given an open cover of Y, Wi, be an open cover. So then Wi is equal to Y intersection Ui for some open set Ui in X. So our picture, it looks like this. These are X and this Y. So we are given some open cover. So these are the UIs. So this implies that Y is contained in union I in I, Ui. And this implies that we can write X is equal to union I in I, Ui, union with X minus Y. And notice that this set is open as Y is closed. So by compactness of X, this has a finite subcover. So let us say X is equal to Uij, and then we can put an extra X minus Y if needed. I mean, this is true. Although we may not need this extra thing, but okay, there's no problem if we put it. And then we just intersect both sides with Y. So intersecting, we get Y is equal to union Wij. So this proves Y is compact. So it has a finite subcover, and so it is compact. And here is another proposition. Let X be a topological space and let Y contained in X be a compact subspace. Then Y is closed in X. So let us prove this. So we shall show that X minus Y is open. So let X be in X minus Y and let Y be in Y. So that means, because now we are assuming that all our sets are Hausdorff, so X is Hausdorff, so there is open sets like this. So there are open sets uy containing X and vy containing Y. So this we call uy. So X is fixed, and this we call vy, such that uy intersection vy is empty. So as y is compact, well, before that, the vy's, the vy form an open cover for y, and as y is compact, there is a finite subcover. So we can write y as union j equal to 1 to n vyi. So we let u be equal to intersection u y I. Okay, so this is I, not j. So clearly u is open and contains X. So u intersection I equal to 1 to n v yi is contained in u intersection v yi, which is contained in uyi intersection vyi. But this, each of these is empty, so this is empty. So this implies that u intersection y is empty, as y is contained in this union. So this shows that u is contained in X minus y. Thus, X minus y is open, which proves the proposition. So finally, we will prove this well-known theorem. Let y contained in Rn. We will use all this be a subspace. Then y is compact if and only if y is closed and bounded. So proof. So let us first assume that y is compact. Then y is contained in these balls around the origin. In fact, this union is all of Rn, and so there is a finite subcurve. But each of these balls, b0n is contained in b0n plus 1 and so on. So this implies there is n such that y is contained in b0n. So this implies y is bounded. And by the previous proposition, y is closed. Conversely, if y is closed and bounded, then using boundedness, we can find m in natural numbers such that y is contained in minus mm this. So we already saw that minus mm, which is homeomorphic to 0 1, is compact, and so its product is compact. So y is closed in Rn implies y is closed in minus mm to the n implies y is compact. Using the above proposition, which says closed subspace of a compact space is compact. So we will end this lecture here.